Okay, in this video I'm going to continue some short videos on switching. This is the fourth one. And in this one I'm going to help a little bit with some of the homework problems. I think that homework problem 1 and homework 4 asks you to sketch a three-stage switch given n, little n, and k. And then it asks how many simultaneous connections, and then finally is the switch blocking, rearrangeably, non-blocking, or strictly blocking. Well, here I've given, in the previous video, I gave the criteria for strict sense non-blocking, rearrangeably non-blocking, and blocking. And so you can just use the k and the n to figure out which of these cases holds. If it says here, if it's rearrangeably non-blocking, find an example that illustrates how a new connection may force rearrangement. Well, that was also illustrated in the blocking example of the previous video. So that should be fairly straightforward on problem number 1. Problem number 2 asks you to write down some equations, and let me just remind you on the three-stage Clauss switch. That's this basic design we've got here, where we've got 3 stages, an input, a center stage, and an output stage, that the number of switching elements okay, so first of all, this three-stage Clauss switch is characterized by n, and k. And given those 3 values, we can calculate the total number of 2 by 2 switching elements. Okay, so m is equal to the total number of 2 by 2 elements in this switch. And this m we could calculate, and we did calculate, and it's 2k times big N plus k big N squared over little n squared. Okay, so this is the equation that is used to calculate the total number of switching elements. We found that for non-blocking, for strict sense non-blocking, we had to make k greater than or equal to 2n minus 1. And so for strict sense non-blocking, we're going to set k as small as possible. So we're going to set k to be so strict sense non-blocking, k is greater than or equal to 2n minus 1. Well, let's set it equal to the smallest value possible, which is 2n minus 1. So we're going to set k equal to 2n minus 1, and that will, if we plug that value into this above equation, then we get the m value for the strict sense non-blocking case. And that comes out to be 2n minus 1 times the quantity, 2n plus n squared over n squared. Okay, this is given on one of the slides. Okay, now it turns out that we still have, even if we choose k to be 2n minus 1, we still have little n as a parameter we can choose. Okay, so we can still choose little n here. And so what we're going to do is we're going to take this equation and differentiate it with respect to little n and set it equal to 0. And that will give us the minimum number of total switching elements, capital M. And that gives us that n is equal to the square root of big N over 2. So for example, if big N is an odd power of 2, so suppose that n is 2 cubed, then I get little n is the square root of 2 cubed divided by 2, or the square root of 2 squared, which is 2. If capital N is 2 to the 5th, then little n is 2 to the 5th divided by 2, or square root of 2 to the 4th, which is 2 squared, which is 4. If n is equal to, for example, 2 to the 9th, which is 512, then little n is equal to 2 to the 9th divided by 2, which is square root of 2 to the 8th, which is 2 to the 4th, which is 16. Okay, so for any given capital N, you can calculate the little n, which minimizes the total number of switches capital M. So this n minimizes the total number of 2 by 2 elements. Okay, and if you go ahead and plug this n into this equation up here for M, you get, and do some approximations. Okay, so we're going to plug n, so let me do that down here, is equal to square root of n over 2 into the equation M is 2n minus 1 times the quantity 2n minus n squared over n squared, and we get that this optimal switch design for the strict sense non-blocking case is approximately equal to, and I'm not going to go through all the math here, 4 square roots of 2 times n to the 3/2. And this is a great result because, so this is the optimal strict sense non-blocking Clauss switch. A great result because this shows that the total number of switching elements, M, grows as the 3/2 power of the capital N. And that contrasts with the original design, which is all the way back here in the first video that I did on switching here, where if we have an n by n switch, then M is equal to n squared, which is increasing as the square of the capital N. This only increases as the 3/2 power. Okay, the ratio of the square, n squared, to n to the 3/2 is the square root of n. In other words, and the square root of n grows with n. So as n gets larger, the square root of n gets larger. And that means the ratio of the number of switches for the optimal strict sense non-blocking Clauss switch to the straight matrix is growing. So the larger the switch, the more savings you get by implementing these fancy designs. I'll end there.